part two of mineral classification. We did the first half yesterday, and now we're going to continue on today. So here's our 12 different groups that we've identified. And the first group is called native elements. Second group is sulfides. The third group is sulfur salts. The fourth group is oxides. Then hydroxides. The sixth group is the halides. And then we got the seventh group is the carbonates. This is now the second row here. The eighth group is phosphates, chromates, tungstates, and molybdates. The ninth is borates and nitrates. The 10th is sulfates. The 11th is silicates. And the last one is mineraloids. So let's just talk about these here right now. We'll start with the first row. So the first row is native elements. And these are single elements. There's only one element in the whole thing. And I have one example for each group. And I'll point out that they've grouped them by the chemical composition, and specifically by the kind of anion there is. So anyway, so let's just take a look at our native element here. And this is graphite. So if I grab my graphite here, I'm going to put this under the microscope just so we can see what it looks like up close. And let's move that out of the way there. So this is the graphite. And this has basically the chemical formula is just carbon. That's all it is. It's just pure carbon. And I'll show you the carbon atom here. See, it's got 2 electrons in the inner shell and 4 in the outer shell. And that's the carbon. And what it does is these carbon atoms in graphite, they form these layers. And I'll just show you how that works here. Here's a picture of the carbon layers. And you can see each carbon, every ball layer is a carbon atom. So every ball is connected to 1, 2, 3 other carbon atoms. And it just forms a layer, and the first layer is a blue layer, and underneath that, the orange layer is exactly the same carbon atoms. And then you can see how each layer is highly connected to other atoms in the layer. And that gives the property of graphite is essentially you can write with it. And so that's carbon. And anyway, so let's move on to our next element here. And the next one is the sulfides. All right, if you look over here, this is, oh, that's the wrong book. The sulfides. And the sulfide is, has a sulfur ion. And if you look at sulfur on the periodic table, here's sulfur on the periodic table. You notice it's atomic number 16, and it's over there in column 6A. So if you look at the sulfur atom, you notice it's got 6 electrons in its outer shell, 6 valence electrons. And what it wants to do is get 8. So what it will do is add 2 electrons. It will capture 2 electrons and becomes an ion, S2-. So that's why I show here S2-. And now the example I have for sulfur is this is a galena. So let me go put the graphite back here. I'll take a galena, and it feels very hefty. Galena is a very heavy element. And basically what it is lead sulfide. So it's got, the chemical formula is PbS. And it's, so it's got the lead there and the sulfide. And okay, so let's move on to the next one here. The next group is the sulfur salts, and these basically have either sulfur or selenium as a salt. And I actually don't have an example of this. The example I'm using is stephanite, which has a formula Ag5SbS4. So it's got silver, it's got tin, and it's got this sulfur in it. So I just have as a stand-in here. I don't really have that to show, so I picked this one here. This is the silver dollar because that's stephanite. So here's the silver. Because the stephanite is actually an ore of silver. So you can take that and refine it into silver. Okay, so let's move on to the next one. The next group is the oxides. And go back here to this chart here. And that's an O2 ion. So the anion is O2 minus. I said O2, I meant it's O2 minus. So again, if you go to the oxygen, here's oxygen. You notice it also has six electrons in the outer shell. So it'll grab 2 and become an iron. And what it will do is form sulfur oxides. And my example here is corundum. So that's the fourth number here. And I'll take that corundum and I'll put it underneath this. So there's corundum. And so corundum is actually aluminum oxide, Al2O3. And I think I might have, no, it's aluminum oxide, Al2O3. And you're probably familiar with corundum. I mean, they'll take it and use it for sandpaper. They'll grind it up, and it's a very hard mineral. And they'll use it as sandpaper. They'll use it as emery boards. But it also ends up being some gemstones. And okay, so that's the corundum, which is an oxide. Okay, so let's go. We'll put that back in its place, and we'll take the next group here is the hydroxides. So we'll grab that guy here, and I'll put that hydroxide here. And this one happens to be bauxite. And I just want to mention to you about bauxite. If I go to this list here. Right, the hydroxide is the OH minus, and I think I have a picture of a hydroxide here. So here's a hydroxide ion. So it looks like an H, and you notice the oxygen has 8 electrons around it, and with 2 of them it shares with the hydrogen, so it's a covalent bond. And what happens with this bauxite, now, it's actually not a mineral in itself. It's actually a mixture. So this is bauxite here, but it is actually a mixture of several different minerals, and one of which is gibbsite, which is aluminum hydroxide, AlOH3. So this is what aluminum hydroxide looks like. See, it's aluminum and 3 hydroxide ions get together and they form aluminum hydroxide. So this is just one of the elements, or one of the minerals that's in bauxite. And bauxite, of course, is an ore of aluminum. So they can actually smelt aluminum out of this material. So there's our bauxite. Okay, so let's go back. Let's go on to the next one. So the last element in this row here, I've got, this is a halide, and this is called fluorite. So if I go back to this chart here, you can see the halides, number 6 there, is they have the halogen gases, fluorine, chlorine, bromine, or iodine. And what I'll do is I'll show you on the periodic table where those things live. It's on the far right, the next to last column is column 7A, fluorine, chlorine, bromine, iodine. And you may notice then that if I look at the electron configuration, there's 7 elements, or 7 electrons in its valence, 7 valence electrons. And also, same as chlorine, and that's the only ones I have on this list here. So these have 7 valence electrons, so they will form the halides. And so my example here is calcium fluoride. Let me see if I have calcium here. Here's calcium. So these are going to be, the fluorine is going to be -1, and the calcium, you notice it has 2 electrons there. So that's going to be a +2. So that's why you'll see it combined with fluorine, with 2 fluorines. So it'll be CaF2 is the formula for that. So here's our fluoride. Okay, let's go back to the chart here. And so we'll start in the next row here. And the next one up is a carbonate. And this is called calcite, and this formula is CaCO3, so it's calcium carbonate. And the calcite group, or the carbonate group, has the anion CO3 2 minus. So I think I have a picture here of a carbonate, and basically this is what carbonate looks like. This is like a 2-dimensional drawing of it. So there's a carbon in the middle, and this is surrounded by 3 oxygens. And remember how this works is if you look at the carbon has 4 valence electrons, and if we go to oxygen here, it has 6 valence electrons. So oxygens will form a oxygen 2 minus, so that'll give it 3 times 2 is minus 6, and then it'll combine with these carbons, and you'll get the carbonate, CO3, and it's 2 minus, so it's a slight imbalance there in the charge. So that's how you get this carbonate here. So this is one of the most well-known minerals, calcium carbonate or calcite, and so that's group number 7 there I've got. Okay, next group is, put the carbonate back here. Next group, and you may notice I have a little piece of jewelry or something here. And the next group is, let's go to the list here, is the phosphates. And it turns out it's actually more than just the phosphates. It's the phosphates, the arsenates, and the vanidates. So what happens is the phosphates, it forms these this little radical here, or ion, phosphate in the middle there, and it's surrounded by 4 oxygens, and that's the way the phosphate forms. And you notice the oxygens have a minus sign on it, so this is a phosphate 3 minus. Well, it turns out you can do exactly the same thing with the arsenic. You just replace arsenic in the middle there, and it does exactly the same thing. That's why it's in the same group. There's the phosphates, arsenates, and another one's called vanidates. It'll also do that one too, but I don't have a picture of that. So anyway, here's my my example for the phosphate is turquoise. And turquoise has this kind of complicated chemical formula. But I'll put this turquoise piece of jewelry here. And if you look at that, you can see a bunch of crystals there. And that's actually crushed turquoise. And you can buy this if you want on eBay or Amazon. And you actually get these crushed turquoise. So that's exactly what you see in there is crushed turquoise. And that's our example. And again, if we look at the formula, it's got the PO4 in there, so it's got the phosphate, but it's also got a hydroxide in there, and it's got aluminum, and it's got copper. So CuAl6, PO4, 4 of those, and 8 hydroxides. And it also has 8 H2O molecules in there. So that's turquoise. I guess we could look at this a little closer there. So you see the crystals there. Those are the, this is crushed turquoise. Okay, so we'll put that back here and move on to the next mineral. Okay, next one is in the list with the borates. Let's go to that one here. So this is called the borates and the nitrates. And basically the borates have borax and oxygen. And an example I'm using here is borax, which is Na2B4O5OH4. So there's borax. Now it turns out I'm kind of cheating here. This is just a space holder. I don't actually have any borax. So I just put this little bottle cap here in a placeholder for it. I put some salt in it because it kind of looks like it's a white crystal. So you wouldn't be able to tell it much difference from salt. So that's the borates. And the same thing can happen with nitrogen too. So that's what I call it, the borates and the nitrates. Okay, so let's go to the next guy on the list here, and that's the sulfates. So we'll put that under the microscope here. So there's the sulfates, and this happens to be, if you go back to my my chart here, there's the sulfates. I've got gypsum. In fact, let me just tell you what it is. This is actually sulfates, chromates, tungstenates, or tungstates, and molybdates. And I'll show you the way a sulfate looks. Here's a sulfate. And there's a sulfur atom, or sulfur ion, I should say. And then it's surrounded by 4 oxygen ions. And this forms a sulfate group here. And so it's SO4, and it's got a 2- charge on it. So that's the sulfates. And you notice this particular one shows the dimensions there. That's 149 picometers. And a picometer is a trillionth of a meter, 10 to the minus 12 meters. So it's a very small distance there. But you can do the same thing with chromium. So you have these things called chromates. And it's almost the same, it's just that the distance is a little different. See, the sulfate was 149, the chromate is 166. So a little further away. And also we'll do it with tungsten. So there's a tungstate here. And that's this one here. And notice it says W in the middle. That's tungsten for wolframite. And this also has a -2 or 2- charge. And also molybdenum can do the same thing. So these are all in the same group because they're basically all the same, except that the atom that's in the middle there could be either sulfur, chromium, tungsten, or molybdenum. So my example here is going to be gypsum, which is calcium sulfate. And I'll just show that here. And there it is. I already got it out. So calcium sulfate, that's it right there. Make sure I'm focused here. So there's my calcium sulfate. And it's also called calcite. A little dirt on the back there. And you can see the formula is CaSO4 and 2 H2Os. So that's the sulfate group there. Okay, so let's move on here. And our next group is the silicate group. Now this is actually the most important group. And I kind of saved it to the end because it's the biggest one. And basically it has silica is the anion. And if you remember, I had a picture of silica here. Somewhere I got a silica. See, the silica looks like this. It's silica. In fact, it's not that much different from the sulfates, right? Again, you have an atom in the middle, a silicon, and it's surrounded by 4 oxygen ions. And this one happens to have a 4- charge. So, but that's the 2-dimensional drawing of it. In 3 dimensions, remember, it kind of looked like a tetrahedron. So here I show you a picture of this tetrahedron here. And again, you have the oxygen, the silicon ion in the center, which is a 4+ ion, and it's surrounded by 4 oxygen ions, which each 2-. So if you add those up, so this is the kind of what it looks like. It's this tetrahedron. It's sort of a pyramid shape. And it's actually easier to understand if you look at it. This other picture I had explains it a little bit better. Right? This one shows how the silicon's in the middle of a cube, and then the oxygens are on 4 of the corners. And if you just kind of rotate a little bit on its side, you can see how it actually is a tetrahedron shape. And that's what this is here. And we'll get into this. We're going to do a separate episode only on silicates. In fact, we're going to have to do more than one. And these will form all kinds of chains and rings and other stuff like that of different shapes of their of their crystals. So anyways, that's the silicates. Okay, in my example there, like I said, it was a quartz, which is silicon dioxide. Okay, well, I'll do the final one here. And this is the last group, so we've got 12 groups. And this last group is, believe it or not, it's not actually a mineral. And they call them mineraloids. And if you remember, there was like, some very specific definitions to make things a mineral. And these mineraloids don't quite meet the definition of this. And this one is actually called obsidian. And it's also silicon dioxide, just like quartz. It's really not that much different. In fact, it could probably go into the silicate category. But like I said, it's not technically a mineral because it doesn't have a crystal structure. They call this volcanic glass. And this particular kind of obsidian is called snowflake obsidian because it's got those that white stuff in there, which I can't remember what that is. But this is the obsidian mineraloid. And like I said, this what it does is this stuff cools very quickly when it comes out of a volcano, and so fast that there's not even microscopic crystals form. It just it immediately solidifies, and glass is basically not a crystal. So okay, so that's our pretty much our presentation here. So we'll put this back. I think I covered mostly what I wanted to cover here.